Our entire world runs on systems we just expect to work, from the power grid keeping our lights on to the apps on our phones. But here's the thing. Every single one of those systems, no matter how perfectly we build it, is eventually going to fail. So the real question isn't if they'll break, but how. I mean, think about it in your own life. Power goes out, do you have a flashlight? Your laptop crashes, did you save your work? Right? We all have these little backup plans, but what about the huge systems we all depend on? What's their plan for when things go wrong? Well, that plan, in the world of engineering, has a name. It's called fault tolerance. It's this whole science of designing systems that actually expect to fail and that know exactly what to do when they do. It's about building things that can handle a crisis and just keep on going. So how on earth does that actually work? Well, it turns out that failure isn't a one-size-fits-all kind of deal. You can actually think of systems as having one of 4 different personalities when it comes to how they fail. And it all boils down to 2 key ideas. Does the system stay working, which we call liveness, and is its data kept safe, which we call safety? First up is the absolute gold standard, masking tolerance. You can think of this one as the superhero of system design. Something breaks, a fault occurs, but from your perspective, nothing happened. The system completely hides the error and keeps working perfectly. Liveness is preserved, and safety is preserved. It's the ideal. The perfect analogy for this is a backup generator at a hospital. If the city's power grid goes down, that generator kicks in so fast that the lights don't even flicker. The life support machines, everything, just keeps running without a single hiccup. To everyone inside, it's as if the failure never even happened. It was completely masked. But let's be real, that kind of perfection is pretty rare and often really expensive. So sometimes, a system has to make a tough call. This brings us to non-masking tolerance. With this one, the system stays online, so liveness is preserved, but its safety might be at risk. It's still running, but it might be working incorrectly, which can be a pretty dangerous game. A good example here is a simple uninterruptible power supply, or UPS, for your computer. When the power cuts out, the UPS battery keeps your computer on, so you have liveness. But the power it's supplying might not be clean. It can fluctuate. So while the computer is alive, it's not entirely safe from potential damage. Now, our third personality is basically the polar opposite. This is called fail-safe progress. And with this one, safety is king. The system's #1 priority is to protect itself and its data. So the moment it detects a serious fault, it just shuts down immediately. Liveness is compromised for sure. The system isn't working anymore, but everything is kept perfectly safe. The classic real-world example is a circuit breaker in your house. If there's a big power surge, the breaker doesn't try to keep the lights on, it just trips. Boom! Cuts the power instantly. It sacrifices liveness to guarantee the safety of your TV, your computer, and every other appliance. It's a deliberate, protective shutdown. And finally, we have the most polite way to fail, graceful degradation. Instead of just crashing or shutting down abruptly, this system takes a moment. It says, okay, I see a problem and I need to stop, but first, let me just finish what I'm doing. It saves its progress to a safe state and then powers down. You see this every single day. It's literally what your computer does when you click shut down. It doesn't just die. It goes through its checklist, prompts you to save your unsaved work, and creates a final checkpoint of its state. That way, when you turn it back on, you can pick up right where you left off. Okay, so we've got these 4 personalities of failure. But how do engineers actually build systems that can do this stuff? What's in their toolkit? Well, it pretty much comes down to 3 core strategies. The 3 big approaches are these. You can just make extra copies of all the important hardware. That's called modular redundancy. You can have different teams of programmers build their own solutions to the same problem. That's end-version programming. Or you can use some really clever math in your code to find and fix errors as they happen. That's called error control coding. Let's dig into modular redundancy. This is kind of a brute force approach, but it is incredibly effective. For something critical like the space shuttle's flight computer, you don't just have one, you have several, let's say 3. They all get the same input and do the same math. Then a component called a voter compares the 3 answers. If one computer glitches, the other 2 outvote it, and the system uses the majority answer. The error is completely masked. And version programming takes that same idea and applies it to software. You give the exact same problem to several totally independent teams of programmers. The bet you're making is that they won't all make the same mistakes or introduce the same bugs. Then you run all of their programs at once, and a voter picks the most common and hopefully correct result. But here's the crucial trade-off. cost versus reliability. Making multiple copies of hardware or hiring multiple software teams is insanely expensive, but it gives you the best possible reliability. On the flip side, error-correcting code is much, much cheaper to implement, but it only offers moderate protection. This is the constant balancing act for engineers. How much reliability can we actually afford? Okay, now things are about to get even more complex. It's one thing to make a single system resilient, but what happens when you have a whole network of computers that all have to work together? They all need to agree on a single source of truth, even when some of them might be failing. This is known as the problem of consensus. Consensus is, and I'm not exaggerating, the bedrock of our modern distributed world. Think about a bank's database. Every computer in its network has to agree on your exact account balance. If they disagree, it's chaos. A consensus protocol is the set of rules that guarantees all the healthy computers in a system will arrive at the exact same decision. For any consensus algorithm to actually work, it has to follow 3 absolute ironclad rules. First, termination. The process has to actually end. It can't just debate forever. Second, agreement. Every healthy computer must agree on the exact same decision. And finally, integrity. The decision they land on has to be a valid one that was actually proposed in the first place. But what if some of the computers in our network aren't just broken? What if they're actively malicious? What if they're trying to cause chaos? What if they lie? This brings us to the final boss of fault tolerance, a famous thought experiment called the Byzantine general's problem. So, imagine this. There's an army surrounding a city, split into divisions, each led by a general. They all need to get the same order from their commander, either attack or retreat. If they all attack together, they win. If they all retreat together, they save their army. But if it's a mix, it's a total disaster. The problem is, one of the generals is a traitor. The commander sends the order attack to everyone. The loyal generals get the correct order. But the traitor deliberately sends conflicting messages. They tell some generals to attack, and they tell others to retreat. This creates total confusion, paralyzes the army, and guarantees failure. And this isn't just some ancient military puzzle. This is the exact problem that modern systems like blockchain have to solve every single second. A blockchain is just a big network of computers that don't know or trust each other. So to add a transaction, they have to reach a consensus, even though some of them might be traitors trying to cheat the system. At the end of the day, these principles are more critical than ever as we build more and more complex systems. From networks of self-driving cars to global AI models, we have to design them to withstand not just simple failures, but active betrayal. Which leads to the big final question. What is the next great agreement problem that's going to define our future?